three different processes, and let's just talk about them in a little bit more detail, in particular the Compton scattering. I wrote down a formula for you the other day which allows you to calculate the energy of the outgoing photon as a function of the energy of the incoming photon and the angle through which the photon is scattered. Okay? We didn't talk about what is the relative probability for photons to be scattered as a function of angle. And it turns out that can be calculated. This figure is out of Lilly's book, and he refers you to another textbook if you want to see the derivation. It's a complicated derivation, and again, we don't spend a lot of time on that in this class. But the point is it can be done, and the result is shown here, that what's being plotted here is the cross-section for Compton scattering as a function of the angle of the outgoing photon, and it's being plotted for different energies of incoming photons. So E equals 0 means very, very low energy photons. What you see is a cross-section which is symmetric about 90 degrees. In other words, the probability for the photon to scatter through 0 and 180 degrees are equal, and there's a minimum at 90 degrees. As you go higher and higher energy, the cross-section peaks at smaller and smaller angles, meaning it's much more likely for the photon, the secondary photon, to keep on going in the general direction the incoming one was. And there's less and less of a chance for large angle scattering. And that's fairly characteristic. So at low energies, you're going to see a lot of backscattering. That'll turn out to be interesting later on when we have some detectors in here to look at. We try to understand the spectrum that we see. But in general, for higher energies, meaning MEV type energies, the scattering is mainly in the forward direction. And so that will influence the energies of those outgoing photons because the energy is obviously a function of that angle. Okay. We talked a little bit about neutrons and how they interact with matter and the fact that they get attenuated as they pass through matter. And exactly the same thing happens for photons. So what's being plotted here is a couple of different experimental situations where you have a source labeled S over there. In this case, of something that's emitting photons or gamma rays. In the drawing on the left, they've got a collimator, meaning something that allows you to filter out gamma rays that are going off in all directions except the one you're interested in. So often it would be a block of lead or something like that with a small pinhole drilled through it. And then the gamma rays that come through the pinhole then emerge and hit some target material. And as they go through this target material, this rectangular piece over here, they interact via Compton scattering, photoelectric and pair production, and not all of them make it through. And if we have a detector over here, we can measure the number of particles that make it through for a given number of incoming particles. And what happens is the change in the number of photons going through depends on the kind of factors you've seen before when we've been talking about reaction rates and cross-sections. So this is the change in the intensity, if you like, per unit thickness dx of the target we're talking about. And it's going to depend on how many target nuclei or how many target atoms there are. And in the way this is written, this number is expressed as a number per unit volume. So it's the number of atoms per cubic centimeter in the target. It depends on the cross-section. And now the cross-section in principle is the sum of cross-sections. Okay? Because in general, the photons will interact by the photoelectric effect, the Compton, and pair production if they have high enough energy. And the way Lilly writes down the Compton scattering cross-section, he does it per single electron. And if you've got a target that has an atomic number of Z, then there'll be Z electrons per atom. And that's why that factor of Z is there. And then you can integrate this expression. So this is di dx is n sigma I. And it looks like the exponential decay law once again, which is exactly what it is. And so the intensity of the radiation, which in this case are photons, falls off exponentially with the thickness of the material. Okay? And this quantity n sigma is often written as mu. It's a linear attenuation coefficient. And it's a measure of how far you have to travel in a material before the intensity is reduced, in this case by a factor of 1 over E. Okay? And it'll be different for each material. It'll depend on the Z and the A of that material. And it'll also obviously depend on the energy of the photon, because that will affect the cross-section that goes in there. And to show you some more plots of this kind of thing, these are a related mass attenuation coefficient, linear attenuation coefficient mu, and you divide it by the density of the material rho, and you get the mass attenuation coefficient. So This number has funny units. The units, because you're taking a number and dividing it by a density, you get centimeters squared per gram as the units of the mass attenuation coefficient. And these are plotted for two different materials, aluminum and lead, as a function of the gamma ray energy. And you can see that for each of these, there are different regimes where the photo effect, the Compton, and the pair production are the dominant way in which the photons interact. You can see for aluminum, the photo effect pretty much is over with by about 200 keV or 0.2 MeV, whereas for the lead, the photo effect remains dominant up to close to an MeV. Any idea why that might be true? What's so different about aluminum and lead in terms of the photoelectric effect? Pardon? The binding energies of the electrons, exactly right. Okay? The binding energies of even the innermost electrons in aluminum are on the order of 1 keV or less. Okay? Whereas in lead, they're more like 100 keV. And so until you get up to 100 keV or more, you actually can't undergo a photoelectric effect with the innermost electrons in lead. And that's what these edges have to do with. So up here you can see, because it's a compressed scale, you can only see one edge labeled the K edge. That's when you can finally ionize the innermost electron in lead. And that cross-section is large and remains large until you're well above that threshold. So for the lighter materials, the Compton is going to be the dominant mechanism in the regions we care about, namely 100 keV to maybe 10 MeV, whereas in heavier materials, other processes can be dominant. And so you need to look at these cross-sections for the material you're interested in to figure out which is the major way the photons are interacting. This is a table taken out of another book showing what are called half-value thicknesses. This means the amount of material that's needed to reduce the flux of photons by a factor of 2, or to reduce it to half of its incident value. And this is being plotted for different energy photons, and in this case in water. So for example, if I have 100 keV or a 0.1 MeV energy photon, it's going to take about 4 centimeters of water to reduce the intensity of those photons by half. On the other hand, if I have 10 MeV, it's going to take 31 centimeters, and so on. And that's because those cross-sections are falling off as the gamma ray energy gets higher and higher. And if we're trying to achieve the same amount of attenuation, we need more shielding. And so these kind of factors play a role if you're trying to design, let's say, an accelerator facility where you're going to make a lot of radiation, let's say photons, and you want to shield people against that. Or you have a nuclear reactor and you've got nuclear fission going on, generating neutrons and gamma rays, and you want to make sure the operators of the reactor are not going to get fried by that radiation. You need to consider how much shielding material you need to put between them and the source of the radiation. So this has real practical importance. Those attenuation coefficients you can look up. You can go online and look them up. There are tables of them. You don't have to calculate them for first principles. There are lots of sources to find those things. Another type of radiation we talked about and discussed how it interacts with matter are electrons. So I'm switching gears now from photons to electrons. And again, electrons produce ionization when they pass through matter. And typically they interact with the electrons and knock electrons off of neutral atoms and create ions. But another kind of interaction that we talked about was called bremsstrahlung. And this is an example of the energy spectrum of this breaking radiation. So the electrons are passing through some material. In this case, they're running through aluminum. And as they scatter, they are being accelerated. And because an accelerated charge produces radiation, they produce this so-called bremsstrahlung radiation. And what's being plotted here is the spectrum observed when electrons produced by the beta decays of strontium-90 and yttrium-90 pass through aluminum. And so this is now the number of photons, X-rays, as a function of their energy that are produced by those betas interacting in the aluminum. Okay? And you can kind of see that there are two different spectra here. There's one which is intense at low energies and falls off by, say, maybe 400 keV. And there's another one which extends much higher in energy. And that's because of the nature of the source that was being used to make this. This is an interesting radioactive source, which is one of those ones that get used to generate electrical power. This is often the source in a nuclear battery. Strontium-90, we'll see later on, is one of the long-lived fission products. It gets made in large abundances in nuclear reactors. It has about a 30-year half-life. It's a pure ground state to ground state beta emitter. So the ground state of strontium-90 decays directly to the ground state of yttrium-90 with an endpoint energy of 546 keV. So that means when the strontium undergoes the beta decay, there's a distribution, you all know this now, there's a distribution of beta energies that go from 0 up to 546 keV. So imagine you are a 546 keV beta running through aluminum, and you undergo a scattering. What's the maximum energy X-ray or photon you can possibly produce? You have 546 keV of kinetic energy available to you. The most you can do is lose all of it, right? Okay, you can't lose any more than that. So the maximum possible energy Bremsstrahlung you could get from such an electron is 546 keV. And that's a very rare thing to happen, right, to lose all of its energy in one radiation event. So that's why this spectrum down here stops at very low energy. That's from the Bremsstrahlung produced by the betas from strontium-90 decay. On the other hand, once the strontium-90 beta decay has happened, you produce yttrium-90, which is also radioactive, undergoes a pure ground state to ground state beta decay, but this time with a much higher endpoint energy, 2282 keV. And those electrons also interact with the aluminum, and they can produce much higher energy Bremsstrahlung. So that's why you see two components of the spectrum. Okay. Is there a question? Okay. So that's Bremsstrahlung. The scattering of electrons off electrons and Bremsstrahlung were the two ways we talked about electrons interacting with matter and losing energy. In fact, there's another way, which is important mainly for very high energy electrons, and this has to do with what's called Cherenkov radiation. The idea here is that if you have a charged particle, and it doesn't have to be an electron, and this drawing talks about muons, but any charged particle, moving through a material with a velocity that's greater than the speed of light in that material, this kind of radiation called Cherenkov radiation is produced. Now, you may think, wait a minute, this is crazy. Nothing can move faster than the speed of light. Isn't that what Einstein said? And the answer is, well, he said it, except what he really said was you can't move faster than the speed of light in a vacuum. That's the ultimate speed limit as far as we know. But in matter, light travels slower than it does in a vacuum. And the usual medium in which we deal with this is water. Okay? And in water, light travels about 1/3 slower than it does in air. And so there's nothing that prevents an electron, or in this case a muon, moving faster than the speed of light in water. That doesn't violate special relativity or anything else. When that happens, an electromagnetic shock wave gets produced, analogous to a sonic boom, but this time it's electromagnetic radiation rather than sound waves. And you get this Cherenkov radiation emitted along the direction of the incoming charged particle, in this case a muon moving faster than the speed of light in water, and the radiation comes off in a cone, very much like a sonic boom does. It goes off in the forward direction with an opening angle, which is actually a measure of the velocity of the particle that's moving. And so you get this this is visible radiation. You can actually see it with your eye. And it's often used as a way of detecting very fast-moving charged particles in material. In fact, if you've ever visited a nuclear reactor, you've probably seen something that looks like this. This is a swimming pool type reactor like the one we used to have in our basement. The core of the reactor is sitting down here in a pool of water, and that pretty blue glow is the Cherenkov radiation. Okay? And any idea what's producing it there? What's producing fast-moving charged particles? Fission products, exactly. The beta decays of fission products. So the reactor is producing very radioactive nuclei, most of which decay by beta minus emission. They don't all get stopped inside the fuel or in the core. They make it out into the water, and they generate this pretty blue glow. Okay? And at most reactors, you'll see pools that actually have the spent fuel that's been taken out of the reactor since we don't have anywhere else to store it yet. Those pools glow this pretty blue glow. It's kind of pretty until you realize you can't turn it off. It's a little bit scary, actually. Okay, so that's Cherenkov radiation. We also talked about the fact that with these different kinds of radiation interacting with matter, and because of their charges, their masses, and so on, that there are very different amounts of ionization that get produced per unit length, and as a result, there are very different ranges for these types of radiation. And again, I think on the first day I did those little demonstrations with a Geiger counter and sources of alpha, beta, gamma radiation, and showed you how much material it took to stop each of them. And this is a table just being a little more quantitative about that, showing for 3 different kinds of radiation, in this case alpha, protons, and electrons, which all start out with 5 MeV of kinetic energy. This is called the specific ionization in air, and what that means is the number of electron-ion pairs that get produced per centimeter of material that the radiation traverses. So for example, for alpha particles, you get 40,000 ions per centimeter as the alpha goes through the air, whereas for a same energy proton, the specific ionization is much less. It's 4,200 ion pairs per centimeter, and for electrons, it's even smaller. That translates into very different ranges for these things. Remember, the range is the distance it takes to fully stop the particle. So with a very highly ionizing particle like the alpha, it doesn't take very much material to stop it. And you remember from the first day, it took a single sheet of paper to stop an alpha whose energy was about 5 MeV. And here it's showing you the range in air, and then similarly in water. And the major difference between the air and the water is the density. Okay, the density of air is very low, so it takes a lot of centimeters, but in terms of the amount of material that you need to traverse, it's not so different for air and for water. For protons, again, because the ionization is higher, the range, the ionization is smaller than it is for alpha, so the range is larger. And finally, for the electrons, because the specific ionization is so much lower, the range is a lot higher. So depending on the type of radiation you're dealing with, you'll have to figure out how much shielding you need. And it'll be different for the different kinds of radiation, even if their energies are very similar, okay? Because the specific energy loss is very different for the different kinds of radiation. Okay, so let's get back to the question earlier about neutrons. We were asking about what is ionizing radiation. And the question is, are neutrons a form of ionizing radiation? So let's discuss that. Do neutrons produce ionization directly? I see head shaking no. No, they don't. Why don't they? Well, almost. So the one exception to that, I would say, is the photon. Right? The photon we consider to be ionizing, even though it doesn't carry a charge. But that's a little bit of a cheat because it's interacting via the electromagnetic interaction, okay? And that's how it rips the electrons off. But how do neutrons interact with matter? What of the 4 forces do they have available to them? The strong nuclear force, right. And that directly doesn't produce ionization. So how do neutrons lose energy as they're traveling through matter? They scatter via the strong nuclear force, okay? And what are they going to scatter off of? Nuclei. And what's going to happen to those nuclei once the neutrons bounce off them? They're going to move through the material. And so it's the scattered nuclei which are actually going to produce the ionization. So for example, if you have neutron scattering on hydrogen, the lightest possible target you could have, you're going to produce recoiling protons. And those protons then lose energy via the mechanisms we've just talked about, and they produce ionization. So this is a sort of tricky question, and on a lot of radiation safety exams, the people who write the exams don't quite get this distinction. I would say neutrons are not ionizing radiation, at least not directly, but they produce ionization through the secondary particles they collide with. So, for example, the protons would produce ionizing radiation. Okay. Now, the other day we talked about neutron activation, and I went through one example of how this was used, and this was the problem of trying to figure out what killed Napoleon. And I mentioned that there's another problem I'd like to talk about, and so let me do that today, and that'll finish up the discussion of neutron activation analysis. And this has to do with what killed the dinosaurs. So let me just remind you of the idea of neutron activation. You have a target, Z and A, and you add a neutron to it. So you don't change the Z, but you increase the number of neutrons by 1 unit, and so the A goes up by 1 unit. And gamma rays are produced when that happens, because what you're doing is you're creating a new nucleus, the A+1 nucleus, but you're creating it in a very, very highly excited state. You're creating it in a state right at the neutron separation energy because you've added a neutron, let's say 0 kinetic energy to it. And so that highly excited compound nuclear state that we've created decays, and often decays by emitting gamma rays, and those were called prompt gammas because those are emitted during the reaction, okay? And there is a way to do prompt neutron activation analysis, and I showed you some of the spectra the other day. The more conventional way to do it is to do the irradiation and then turn the neutron source off and utilize the fact that most of the nuclei you produce as a result of the neutron capture are radioactive. They undergo beta decay, and very often beta decay to excited states which emit gamma rays. This turns out to be a much simpler way to do things experimentally because you get away from all the radiation produced by your... And so you look for these beta-delayed gamma rays, and the feature that we utilize is the fact that each nucleus has a specific set of nuclear gamma rays that allow you to identify the Z and A of the nucleus that's producing them and work backward to figure out what the parent was and work further backward to figure out what the target must have been that captured the neutron. Okay. And just to show you the kind of sensitivities you can get, neutron activation analysis is one of the most powerful techniques we have to do elemental and isotopic identification. So this is a table trying to show you the sensitivities, and these sensitivities are given in the number of micrograms of material you need to actually produce a usable signal. And the point is, some of these are incredibly small, 10 to the minus 6 micrograms. So that's 10 to the minus 12th grams of material is all you need to be able to see manganese, for example. We do a lot of this in our research where we're, in this double beta decay experiment I've mentioned, where we're very concerned about sources of background radiation coming from the decays of uranium and thorium. And so we do neutron those isotopes, and the sensitivities we can get are even smaller than that. So it's a very, very powerful. It depends on the particular element in terms of its isotopic abundance, in terms of the cross-section, the lives of the things you make. So it isn't a universal technique that works for all elements and isotopes, but for a lot of them, something like 57 or 58 of the naturally occurring elements, this is probably the most sensitive technique you have. And this just shows a spectrum sort of like the ones you saw the other day. It's again a gamma ray spectrum taken following neutron activation of a hair, a human hair. And this one isn't so sensitive to the arsenic. This is modern hair, and we don't have as much arsenic as Napoleon did, but it still shows up. But you see things like zinc 65, gold 198, and so on. And these are at the micrograms or smaller level in a sample of a hair. Okay, so it's a powerful technique, and you're wondering, well, what does this have to do? It's the way we figured out what actually killed the dinosaurs. And what's nice about this story is it happened right here in Berkeley. This gentleman, Louis Alvarez, was a professor in the physics department here, and this is his son, Walter Alvarez, who is a geologist. And Louis was interested in all kinds of things and knew an awful lot about all aspects of physics. His son was the geologist, and his son was excavating over in Italy, and he came across a formation which doesn't show up so well here, but there's a bunch of rock layers which you can see running in this direction, and there's another bunch of rock layers there, and in between there's a little tiny layer of clay. And it shows up better over here. This is someone who followed on the work that the Alvarezes did. This is in Antarctica, and here you can see more clearly a bunch of rock down here, a bunch of rock up here, and this is the clay. Okay? And what these guys discovered is that if you look in these rock layers for fossils, the dinosaurs are found down here, and there are no dinosaurs here. Okay? So something happened in between here and here, and the question was, what was it that made the dinosaurs disappear? And Alvarez's idea was it had something to do with what was in that clay. Okay? And this just shows you a little bit of the history of life on Earth. This is a measure of the number of extinctions per. So here we are today. This is going backwards in time. And, you know, species evolve and die all the time. And there's more or less a continuous distribution of extinctions, except every once in a while there are peaks. Okay? So back here at this event, this is when the dinosaurs died, right here, about 65 million years ago. At the boundary between two layers called the Cretaceous period and the Triassic. And so there was an enormous rate of extinctions that happened right then. And there were other extinctions further back in time, but this is the one we're going to concentrate on now because the dinosaurs were living in here and they're not living after that. What Alvarez started thinking about was maybe there is some extraterrestrial explanation for this. Okay, maybe something happened out in space that caused the extinction. And the idea he came up with was something came in and caused perhaps an enormous explosion, which eventually killed the dinosaurs. And Louis was very knowledgeable about astrophysics, and he noticed that meteorites and things like that contain a lot of rare platinum group elements which are not so common on Earth. And so he decided to go look at that clay layer to see if he could find evidence for that that would indicate that something from outer space came in and was connected to the death of dinosaurs. And so he made use of neutron activation analysis to do this, in particular using the element iridium. Iridium is a very rare element. It's in the region around gold. In fact, it's even rarer than gold and more expensive than gold. And this shows a part of the chart of the nuclides around iridium. And it indicates why this is a very nice material to look for using neutron activation analysis. In particular, it has this isotope 191 iridium, which is stable and has a 37.3% natural abundance, so there's relatively a lot of it. You can't read this very well from the back, but it also has a very large thermal neutron capture cross-section, nearly 1,000 barns, okay, meaning it has a very high probability to capture a neutron. And when it does, it makes iridium 192, which has a convenient half-life of 74 days or so, meaning you don't have to rush. You can take your sample to the reactor, irradiate the heck out of it with as many neutrons as you can get, bring it back to your laboratory, and at your leisure, watch the decay of iridium 192 and see the gases which are characteristic from its decay. There are a bunch of them that can be used. And so this was done on samples of material that they collected both above and below that clay layer and right in the clay layer. Okay? So the Alvarezes, together with folks at Lawrence Berkeley Lab, did this, and this is what they found. This is a plot of the amount of iridium, and notice the letters down here you can't read, parts per billion. So these are very, very small amounts. And this is plotted against where in the rock strata the sample came from. So down here, this is before the dinosaurs. That's after, this is where the dinosaurs were, sorry. That's after the dinosaurs were gone, and this is a blow-up of the clay layer. And what you can see is very, very small amounts of iridium down here, essentially consistent with zero, then a very large peak right here, and then going back to nearly zero again. Okay? So the evidence was that there was something that came in during this very narrow period in time when the clay layer was laid down that had a lot of iridium in it. Okay? And it was neutron activation that proved this. Now you might think, okay, this is no big deal because this was all just in Italy. Maybe something funny happened in Italy, and that wouldn't explain killing dinosaurs all over the world. In fact, once the Alvarezes reported this, people were looking for this clay layer, and they found it everywhere they looked. Okay? So each one of these dots represents a place around the world where a similar phenomenon was seen, mainly a rock layer with this layer of clay in between and then more rocks above it. And everywhere they looked using neutron activation analysis, they saw the same thing, that there was small amounts of iridium below and above the clay and a large amount in it. And the picture that emerged then was something like this. There was a very large asteroid, something like 10 kilometers in diameter, which came in from outer space and collided with the Earth. The asteroid basically got vaporized in that process and created a big hole in the Earth. And an enormous amount of ash and dust and rock got kicked up into the atmosphere, and that stuff got spread all around the world. And so that's where the origin of the iridium is. The iridium was contained in that asteroid. It got vaporized, spread around the world, eventually came down in the form of ash and dust, which got incorporated in that clay layer. During the time it was up in the atmosphere, the theory is that it essentially blocked out all the sunlight from all this dust. As a result, all the plants died. As a result, all the plant-eating dinosaurs died. As a result, all the meat-eating dinosaurs died. And so that's the theory behind the extinction of the dinosaurs. And it was basically started here in Berkeley, and neutron activation analysis is the way it was figured out.
How did they know that the very good.
Very good. So people began wondering, okay, if this is true, there ought to be a crater somewhere. And there aren't any big craters sitting on the dry land, but they did surveys from space and with sonar from ships, and they discovered just off the Yucatan Peninsula off of Mexico, and that's how they decided that's where it must have been. And in fact, if you look around that area, there are microdiamonds and little glass spheroids which were produced as a result of the collision, thought to be thrown up in the initial impact. And they're pardon?
They get the diameter the same way, like
I think so. I think they get it from that, and also from just the total amount of iridium that got distributed, and how much typically is in something like a meteorite or an asteroid. There are some competing theories. You might have read recently that some folks are questioning whether this is really true. There's another idea that it had to do with volcanic eruptions, which bring large amount of material from the core of the Earth up and also distribute it. And I'm not a good enough geologist to know which is right, but I like this story anyway, because it involves nuclear physics. Any questions about that? Okay, I think with that, yeah, we're pretty much done with the discussion of radiation interacting with matter in terms of the mechanisms by which it happens. What we're now going to do on Friday is start talking about how we want to use the fact that the radiation interacts in certain ways. And in particular, we'll talk about ionizing radiation detectors of various kinds. And I'll bring some in and show you examples of it. Okay? Okay, so we'll quit here for today a little bit early.